This figure shows a single point cutting tool. This is the gripping end and this is the cutting end. Now, what we will have to do is we will have to find out the optimal cross section of this particular cutting tool, whose dimensions are given by B and H and having the fixed length, that is L prime. Now, this optimal design should be such, so that the weight should be minimum and at the same time there should not be any mechanical breakage of this particular the single point cutting tool. Now, to determine the optimal design, now we have already discussed how to solve this particular problem using two traditional tools. Now, the first one was random walk method and the second one was steepest descent algorithm. Now, today I am just going to discuss like how to determine the optimal design of this particular the single point cutting tool using a genetic algorithm. Now, before I go for that, let me show you the mathematical formulation of this particular problem. Now, here our aim is to minimize the mass or the weight of the cutting tool. So, minimize m prime, that is 1572 multiplied by V multiplied by H, subject to the condition that the developed stress, that is 300 divided by B H square, should be less than equal to the allowable stress, that is 150 multiplied by 10 raised to the power 6. So much Pa, that is Newton per meter square, and B is lying between 0.005 and 0.20 meter and H is lying between 0.005 and 0.10 meter. So, this is nothing but a constraint optimization problem. Now, let us see how to solve this constraint optimization problem using a non-traditional tool like genetic algorithm. Now, here I am just going to start with a binary coded GA, that is, if you see the statement of the problem. So, we are going to use a binary coded GA to solve this constraint optimization problem, and I am just going to show some hand calculation considering the population size n is equals to 6. Now, we will have to use tournament selection, then single point crossover with a probability P c equals to 1.0. So, all the mating pairs are going to participate in crossover. Then bitwise mutation with a probability P m equals to 0.01. Now, we will have to design the GA string to ensure the precision level of 0.0015 and 0.0002 approximately in the values of B and H respectively. So, accordingly we will have to select the number of bits. Now, this constraint optimization problem has to be tackled using a penalty function approach, and we are going to use the concept of the dynamic penalty. Like if there is any violation of the functional constraint, so that particular solution will be penalized using the principle of dynamic penalty, and we are going to assume that the constant C, that is equals to 2, alpha equals to 2 and beta is equals to 3. And I am just going to show you like through hand calculations one complete iteration of this particular the binary coded GA to solve this problem. Now, let us see how to proceed with this. Now, to start with, actually what we will have to do is, so I will have to find out first like how many bits to be assigned to represent the real variables in order to ensure their precision level. Now, if I see this particular B, now B is nothing but the width of this particular the cross section. So, what you will have to do is you will have to find out how many bits to be assigned to ensure the precision level in the value of this particular the B. So, what we do is we have already discussed how to find out the number of bits to be assigned. Now, supposing that L1 number of bits are to be assigned to represent B. So, using this mathematical expression that L1 is nothing but log base 2 like B maximum minus B minimum divided by epsilon. Now, let me write it here. Say L1 is nothing but log base 2, then comes your B maximum minus B minimum divided by that your accuracy level or the precision level, that is epsilon. Now, if I substitute all such values like B max is 0.20 meter, B minimum is 0.005 and the precision level epsilon is nothing but 0.0015. Now, if I just calculate, I will be getting log base 2 130 and approximately this is equal to log base 2 2 raised to the power 7 and that is nothing but is equal to 7. So, L1 is 7, that means I am just going to use say 7 bits to represent this particular the B. Now, similarly, I can find out the number of bits to be assigned to represent H. Now, using the same expression like L2 is nothing but log base 2 H maximum minus H minimum divided by the epsilon, and if I substitute the numerical values, I will be getting log base 2 475 and approximately this is equal to log base 2 2 raised to the power 9 and that is nothing but 9. So, we are going to assign 9 bits to represent this particular the H. Now, if this is the situation, so very easily you can find out what should be the length of the GS string. Now, to determine the length of the GS string, so what you will have to do is, so 7 bits I will have to assign to represent L1 and 9 bits we will have to use to represent L2. So, 7 plus 9, the total number of bits in a GS string will be 16. So, 7 are used to represent L1 and 9 bits are used to represent L2. Now, if this is the situation, let us see how to proceed with to determine the real values corresponding to B and H. Now, here actually the decoded value corresponding to L1. Now, if you see this particular binary, for example, this particular binary, the decoded value will be like, so this is nothing but 1 0 1 1 0 0 1, that is 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 3, 2 raised to the power 4, 2 raised to the power 5, 2 raised to the power 6. So, the decoded value will be 2 raised to the power 6 multiplied by 1, that is nothing but 64 plus 1 multiplied by 2 raised to the power 4, that is nothing but 16 plus 1 multiplied by 2 raised to the power 3, that is nothing but 8 and 1 multiplied by 2 raised to the power 0, that is nothing but 1. So, if I just add them, so this will become 80, 88, 89. So, I can find out the decoded value corresponding to this particular your L1. Now, if I have got this particular the decoded value, then very easily I can go for what should be the real value corresponding to this particular decoded value of 89. Now, the real value of B is nothing but, so let me just write down the rule for the linear mapping rule, that is nothing but B equals to B minimum plus B maximum minus B minimum divided by 2 raised to the power L minus 1 multiplied by the decoded value. So, this is the rule for the linear mapping. Now, this I can just use here to find out what should be the real value for this particular the B. Now, here B minimum is 0.005, B maximum is 0.20 and we have got small l is equals to 7 here, there are 7 bits and so 2 raised to the power 7 minus 1 multiplied by the decoded value, and if I calculate I will be getting 0.142. So, this is the real value corresponding to this your the B. Now, once you have got the real value corresponding to this particular B, I can use the same procedure to find out what should be the decoded value corresponding to L 2 and what should be the real value corresponding to this particular the H. Now, if I see the string corresponding to this L 2 is nothing but this. Now, here, so I can just place that your the values for the place values of this particular the bits, and I can find out what should be the decoded value. Now, if we calculate the decoded value following the same principle corresponding to L 2, so I will be getting 343. So, for this 343 using the linear mapping tool, so I can find out what should be the real value for this particular H, and H is nothing but the minimum value of H plus the maximum value of H minus the minimum value of H divided by 2 raised to the power L equals to 9 here minus 1 multiplied by the decoded value, that is 343, and I will be getting 0.069 as the real value for this particular the H. And once you have got these real values for this particular B and H, so very easily I can find out like what should be the value of the objective function. Now, here f 1 is the value of the objective function, that is nothing but 1572 multiplied by B multiplied by H, and if you substitute the numerical values and if you calculate, then we will be getting. So, f 1 is nothing but 15.40 and the unit for this will be the kg. Kg will be the unit for this, because this is nothing but the mass or the weight of that particular the single point cutting tool. Now, I can find out the functional constraint, and we will have to determine the values of this particular functional constraint, and we will have to decide whether it is going to violate the functional constraint or not. Now, if you see the functional constraint, it was something like this, like 300 divided by B H square should be less than equals to the allowable, that is 150 multiplied by 10 raised to the power 6. Now, this is nothing but the allowable stress for this particular the tool material, and this is actually the developed stress due to the bending moment. Now, here if I just substitute, then the left hand side of this particular functional constant, that is 300 divided by B H square, B is 0.142 and H is 0.069 square, and if I calculate, I will be getting 0.44 into 10 raised to the power 6. So, this is the developed stress, and the allowable stress is 150 multiplied by 10 raised to the power 6, and here actually the left hand side is less than the right hand side, that means the design is safe. So, there is no violation of the functional constant, and if there is no violation, the penalty term, that is P, will be equal to 0.0, and actually the modified fitness, that is capital F 1, will remain same as small f 1, and that is nothing but 15.40. So, for the first GA string, I am able to find out what should be the value of the objective function, and that is nothing but the fitness, and what should be your the modified fitness, because here there is no violation of the functional constraint. So, this is the way corresponding to a particular GA string, I can find out the numerical value for this particular objective function, and I can find out whether there is any violation of the functional constraint, and if there is a violation, I will be able to find out the penalty term, but fortunately here there is no violation. So, the modified fitness will remain same as the original fitness. So, corresponding to the first GA string, we are able to find out those values. Now, I am just going to concentrate on the second GA string. Now, I have already mentioned that the population size is equals to 6, that means there are 6 such GS string, and corresponding to the first GS string, we have already calculated the numerical values for the fitness, and now I am just going to see how to determine the numerical value, the value of the objective function corresponding to the second GS string. Now, the second GS string generated at random is something like this. Now, I am just going to use the same procedure. So, to represent L 1, I am using the 7 bits, the first 7 bits, and to represent L 2, I am using the remaining 9 bits, and following the same principle, I can find out the decoded value corresponding to this particular L 1, and this will become equal to 26, and I can use the linear mapping rule to find out the real value for this particular B, and this is coming to be equal to 0.045. Now, once I have got this particular thing, so now I can go for L 2. So, I can find out corresponding to this particular L 2, actually your the decoded value is the decoded value is 37, and corresponding to the decoded value of 37, the real value of H is nothing but this, and this is becoming equal to 0.012. Now, the value of the objective function, that is f 2, is nothing but 1572 multiplied by B multiplied by H, and if we calculate, we will be getting 0.85, and of course, the unit will be the kg, because this is the weight. Now, the left hand side of the functional constant, that is 300 divided by B H square. Now, if I substitute the numerical values for B and H, so I will be getting 46.3 multiplied by 10 raised to the power 6, and once again, so this particular left hand side is less than the right hand side. So, there is no violation of the functional constant, penalty term P will be equal to 0, and the modified fitness, that is f 2, will be equal to the small f 2, and that is nothing but 0.85. So, as there is no violation, so the modified fitness will remain same as the original fitness. So, corresponding to the second GS string, so I am able to determine what should be the value of the objective function or the fitness. Now, let us concentrate on the third GS string. Now, the third GS string is something like this. Now, these 7 bits are going to represent the 7 bits are going to represent the L 1, and the remaining 9 bits are going to represent L 2. Following the same principle, I can find out the decoded value corresponding to L 1, the real value corresponding to this particular the B, and I can also determine the decoded value corresponding to L 2, and that is becoming equal to 13, and I can also find out the real value corresponding to H, that is nothing but 0.0074, and I can determine the value of the objective function, that is f 3 is nothing but 1572 multiplied by B multiplied by H. So, that is 0.22 kg. Now, once I have got this, now I will have to check whether it is going to violate the functional constraint or not. Now, here the left hand side of the functional constant, that is 300 divided by B H square, if I substitute the numerical values, I am getting 288.33 multiplied by 10 raised to the power 6, and this particular numerical value is more than the allowable value of the stress, that is 150 multiplied by 10 raised to the power 6. So, there is a violation of the functional constraint, and if there is a violation, now I will have to find out what should be actually the penalty term, and we have already decided that we are going to use the concept of the dynamic penalty. Now, how to determine the amount of this particular the penalty? Now, as I told, there is a violation of the functional constraint. So, what I will have to do is, I will have to first determine what is the amount of violation. So, the amount of violation, that is denoted by psi is nothing but the mod value of the differences between the right hand side of the functional constant and the left hand side of the functional constant. Now, this left hand side and right hand side, the numerical values if I just substitute. So, this is 288.33 multiplied by 10 raised to the power 6, that is actually the developed stress, and the allowable stress is nothing but 150 multiplied by 10 raised to the power 6. And this particular, the difference could be either positive or negative. So, depending on whether I first consider the developed or whether I consider the allowable first. So, accordingly I will be getting positive and negative, and that is why we consider the mod value of this particular violation, and that this is nothing but this. So, 138.33 multiplied by 10 raised to the power 6. And once you have got the amount of violation, now using the principle of dynamic penalty approach. So, I can find out what should be the amount of penalty. Now, to determine the amount of penalty, we use the expression penalty P is nothing but C multiplied by T raised to the power alpha multiplied by phi raised to the power beta. Now, T is nothing but the iteration number. So, we are just going for the next iteration, and that is why we put T is equals to 1 here and C is put equal to 2. These values are assumed by the user. Alpha is assumed to be equal to 2 and your beta is also assumed to be equal to 3, and this is the amount of violation. Now, if we calculate, so you will be getting the penalty term, that is 10.58 multiplied by 10 raised to the power 24. So, this is a very high value. That means, if there is a violation of the functional constant, that is not a safe design from the point of view of mechanical strength, and that is why. So, that particular the solution has to be penalized. This is not a good solution. So, we will have to remove from the population of the G, and that is why what we do is the original fitness F3 is calculated as 0.22. Now, we go for the modified fitness. Now, this is a minimization problem, weight minimization problem, and that is why this penalty term has to be added. And if you add this particular penalty term, the modified fitness capital F3 is nothing but small f3 plus p, and if I substitute the numerical values. So, I will be getting 10.58 into 10 raised to the power 24 approximately as the modified fitness corresponding to this particular the GS string. So, till now actually we have considered 3 GS string, and out of these 3 GS string, for the first two GS string, there is no violation of the functional constant, that is this and this, and for the third GS string there was a violation of the functional constant, and following the same procedure. So, I can determine I can find out what should be the value of B and H, what should be the value of the objective function, and if there is any violation of the functional constant using the same principle for the fourth GS string, fifth GS string and the sixth GS string. Now, as I told that this population of the binary coded G, that is generated at random, and now we will have to find out the decoded value of these particular real variables, and then we will have to find out the real values of the objective function and so on. Now, for example, I have already discussed for the first GS string, this is the decoded value for B and this is the decoded value for this particular H, and similarly for the other GS string I can find out the decoded values. And once you have got this particular the decoded value, now I can find out the real values for this particular the B. For example, corresponding to the first GS string, the real value for B is 0.142, this I have already discussed. Corresponding to the first GS string, the real value of h is this, and the fitness I have already calculated. There is no violation of the functional constraint. So, the penalty term will become equal to 0 and the modified fitness capital M will remain same as the small f. Similarly, for the second GA string, so this is the value of B, the decoded value of H, the real value, this is the real value for this B, the real value of H, and this is the function value, that is the fitness value, and here there is no violation of this functional constraint. So, penalty term is put equal to 0 and the modified fitness 0.85 is nothing but the original fitness. Now, corresponding to the third GA string, the real value of B is this, the real value of H is this, the original fitness, that is small f, is 0.22, but unfortunately there is a violation of the functional constraint and the penalty term we have already calculated. So, this is the penalty term. So, the modified fitness will be this original fitness plus the penalty term, and approximately that is equal to 10.58 multiplied by 10 raised to the power 24. For the fourth GA string, this is the real value for B, the real value for H, the original fitness. Once again there is a violation of the functional constraint and the value of the penalty term is 5.35 into 10 raised to the power 24, and this is the modified fitness, that is capital F, corresponding to the fourth GA string. For the fifth GA string, so this is the real value for B, the real value for H, this is the value of the original fitness, there is no violation of the functional constraint. So, penalty term is put equal to 0. So, the modified fitness is nothing but the original fitness. For the sixth GA string, so this is the real value for B, the real value for H, and I can find out the value of the objective function. There is no violation of the functional constraint. So, penalty term is put equal to 0 and the modified fitness is 6.25 and that is same as the original fitness. So, for the whole population I am able to find out the fitness or the modified fitness. And another thing I should mention here, now if we see the minimum fitness out of the feasible solutions. Now, here there are 6 solutions out of this particular 6. So, this is not a feasible solution, here there is constant violation, and this is also not a feasible solution, there is constant violation. So, the feasible solutions are this, this, this and this. So, there are 4 feasible solutions, and if I compare the fitness values or the modified fitness values, it is better to compare the modified fitness values, I can find out. So, this 0.85 is the minimum fitness of all the feasible solutions. So, the minimum fitness of the feasible solution is nothing but 0.85. Thank you.